In this video, we are going to learn how to find the domain of a function. So first, let's say we have a function y equal fx. Then we use the notation, the curly df for the domain. So the domain of f is the set of all values for which the function is defined. So set of all the values, set of all the values, or the values for which the function f is defined. So that's how we define the domain of a function. So for all the values for which the function is defined. So there are three type of functions to be considered. So let's write them one by one. So let's call it things to remember. So we're going to start with the what we normally call the most innocent function. So that is what we normally call the polynomial. So the polynomial takes this form. So let's say px is a polynomial. So this is the more simple function. So there's a number and then x to a integer power plus another number x n minus 1. The power goes down. So these kind of functions are what we normally call the polynomial. So and then cx plus d. So the condition is n has to be a positive integer or 0. If it is 0, you get the constant function. So n is a positive integer. So or 0 or 0. So the what is good about this function is, and you can see that since those powers are either positive or 0, there are no reciprocals. You do not get any negative powers, so there are no fractions here. There are no fractions with x. So that means there is no division by 0 situation here, because that's something we try to avoid. We try to avoid division by 0, and you can see that that's not going to happen. And also, since n is an integer, there are no root problems. So there are no square root or any other even roots. So that means there are no problems with this function. So that means the domain is all real numbers. You can plug in any number you want. So that means for this, so this is actually these kind of functions are what we normally call polynomials. So this is a polynomial. So these are called polynomials, and we can learn more about this later. So because of this, the behavior of the function, and you can see that the domain of a polynomial, any polynomial, domain of a polynomial is simply all real numbers. So this is domain is which is a set. So you can see that. So you can say set of all real numbers. This set we normally represent as script R. So that is how we write the same set, but we use this one. So if it's a polynomial, you can plug in any number. So it's set of all real numbers. So let's look at the next one. So the next one is the rational function. So rational function. Rational function. So rational functions means the functions so that are fractions. So we're going to take so that's a rational function which are fractions we write as a ratio of two polynomials. So polynomials we talked about earlier. So what we now get, we divide two polynomials. So these are both polynomials. So that's what we call a rational function. So now the problem is there's no problem from the numerator. There's a problem from the denominator, because the denominator polynomial can be 0. So that's what we're trying to avoid. So that means if it is a rational functions, to avoid division by 0, what we're going to do, so let's call it a rational function, because it's true for any rational function. So if it's a rational function, so I'm just say rational function. So what happened, what we need to avoid is just the x for which the bottom function equal to 0. So we can remove all these values. That's how we find the domain, and we don't worry about the numerator in this case because there's nothing happened there. But if even if you see a common term, so we are not going to do any cancellations for them. So so we do not cancel common terms. So that's something you have to remember, common terms. So the reason is, even though we cancel the common terms, the original function still has that factor. So that means you can still plug in the value. So you can say that, okay, we cancel the term, now there's no problem. That doesn't work like that, because even though we cancel the term, they still, if you look at the original function, that term is still there. So that means you can plug in the value. So that is why we do not cancel. Okay, now the third type, I'm going to divide into two types. So the third type is what we call the radical function. Like roots, radical function. So radical function, what we can do, we can divide into two types. So I'm going to say type 1. So let's look at the type 1 radical. So type 1 radical is, let's say we have y equal, so this is a function. So there's some kind of function there. So it is like x. We can talk about roots, but these are like roots where n is odd. So we're going to consider the first case, n is odd. So that's the first type, n is odd. So let's look at few cases. So if you say n equal 1, that's like you're going to get like some uncommon one. So it's n equal 1. This is actually x. It's not square root. It's x. So, but we know that this y equal x function behave very well. So this is the graph of the function y equal x. That's just a straight line. And then you can see that it's defined for all real numbers. That's a value for all numbers. So let's look at other cases, like what if n equal 3? So for example, y equal cube root. So if you look at the y equal cube root, and if you look at the graph of this function, this is how it behaves. So it's gonna go it's gonna start with go to negative infinity and go like that, and that's the shape of the graph. So and they pass through 0, and you can see that's defined for all real numbers. And again, like if you look at like some other terms, like with larger power, like for example, let's say y equal x to the 7th root. This pretty much 7. So it's pretty much have the exact same form. So if you look at the graph, what happened? It's look like very similar, but it's much more steeper. So that's the only problem. Less steep actually. It's gonna go to 0 fast. We're taking larger roots. So that's the shape of the graph, and you can see that all these graphs pass through 1. So if you plug in 1, you get 1 for all of them. So that's some of the facts that can help you to argue in certain situations. So all of them pass through 1. And then on the other side, if you plug in negative 1, you can see it is negative 1. If you plug in negative 1, it is negative 1. So some of the facts of these graphs. We can talk about more of these later. When you talk about polynomial. So these are some of the facts. So you can see that for these functions, it defined for all real numbers. So that means the domain for these types are all real numbers. So the domain for this, so domain for type 1. So domain for type 1, that means things like 1 is all real numbers. All real numbers. Okay, now let's talk about the type 2. So type 1 is a root with the n odd power. Odd, actually it's odd positive integers, no negative integers. We were talking about roots, not negative powers. Good. So this is about type 2. So type 2, what happened? Type 2. In type 2, like numbers like 2, so that means even power. So like y equal x, even root. So n, n is a positive even integer. Okay, so n is a positive even integer. Positive even integers. So odd integers, we see that is all real numbers. But let's see what happens. Let's look at a few cases. So we can start with n equal 2. N equal 2. So n equal 2, what we get is y equal x2. Well, 2 means the common square root 1. So that is x equal to the square root. But we know what is the shape of the graph. And if you look at the graph, and you can see the part is missing. It's only defined for 0 or positive. So this does not define for negative numbers. It doesn't define negative reals. So that means in this case you can see there's a problem now. So it has to be the greater than or equal 0. So let's look at another one. Let's say n equals 6. Any integer, any positive even integer. So you can see that y equal x to the 6th root. And you can see that we have the same problem. It's again defined only for, it's much more grows slow because it's like the cube root. So so it's like that, and it decay fast. So 0, and then again the same problem is only defined for x greater than or equal 0, and then again we still have the same facts. If you plug in 1, you get 1. That's true. So you plug in 1, you get 1. And also we know that if you plug in 0 for any of these functions with any actually for any root, positive or 0, any root, if n is a positive integer, odd or even, you can see that this is 0. So that's a fact. So that means 0 is there. So but otherwise what will happen is this is the condition. So that means what we have now is the domain of type 2. Domain of type 2 is only x such that x greater than or equal 0. So those are the theories that you need to understand, and you can see that you can do a lot of problems just knowing these 4 facts. So polynomials, it was all real numbers. If it is a rational function, we remove the zeros from the denominator function, not the numerator, just the denominator. And then when you have radical type 1 means odd roots. When you have odd roots, what we do is all real numbers. But when you have even roots, you have to be careful. They look like square root functions, all of them. So that means x has to be greater than or equal 0. So those are the theories. So let's try to do several problems. So we do find the domain of a fx equal x squared minus 5x, and you notice that this is a polynomial. So this is a polynomial. There are no roots or negative powers. So this is a polynomial. So that means the domain, by the theory, the domain of the function is all real numbers. Set all real numbers. So you can say since. So if you write argument, it says since f is a polynomial. Okay. And part B. So let's say we have a rational function. Let's say we have Rx, which is equals to x squared plus 1 over x squared minus 5x, the same function that we have. And you can see that this is a ratio between two polynomials. That's the first polynomial. Qx is the second polynomial. So when you have a rational function, this is a rational function. So you notice that this is a rational function. So when you have a rational function, what we need to worry about is only the denominator function. So we don't worry about the rest. So now what we're going to do is we're going to check. So by the definition, the way we argue, so we see that the domain of R equals to x such that the bottom function not equal to 0. So in this case, what we have is x such that x squared minus 5x not equal to 0. So what we normally do is we actually find when this is going to be 0, because otherwise it's very difficult to find because there are a lot of values. What we're trying to do, we try to find, we set this equal to 0. We set this equal to 0 and find when it is when it is 0, and then we remove those values from the rest of the R. So we do. So the first thing, if you get a problem like that, the first thing would be we try to find factors of this one. So fact, so that's the first fact. In a general problem, that's how we do fact. So we can start with x squared minus 5x. This is very easy to find factors. So x is common, so we're going to pull x out, so we're going to get x minus 5, and then set it equal to 0. Now what we do, we set each factor equal to 0. So you're going to see that the first factor is x, so that means x equals 0. Or the other one is x minus 5 equal to 0. So this can give you two zeros. So factor and then find the zeros. So factor and then the next one is find the zeros. So the zeros are x equals 0 and 5. So that means now what you want to do, and those are the values that makes the denominator 0. So that means your answer now is simply remove those two values. So that means the answer would be x such that x not equal to 0 or x not equal to 5. So that means we just remove those two values from the rest of the domain. So let's also try to graph these answers, because sometimes we need to know how to graph them. So let's graph them. So what we do is, so we have the set of as the number line, so we have all the numbers there. So now what we're going to do is we're going to remove those two numbers. So let's mark them. So one is 0, the other one is 5. This is 0 and 5. What we're going to remove those two, and we have everything else. So that means what we can do is we can draw like a solid line to mean the solution. So but we remove those two numbers. So that's how you graph it. And also we can write the what they call the interval notation. So it's very easy to write the interval notation. So this is negative infinity and this is 0, so let's stop at 0. And then we have the next one, we going from 0 to 5, the other one going from 5 to infinity. Now what we're going to do, we're going to write union and combine them. So so the interval notation, that's what we call the interval notation. So interval notation is, so the domain of f is equals to, we write negative infinity to 0, and then union means O. That means you can pick, so any of them are true. That's what it means. So 0 to 5, and the union, and 5 to infinity. So union means, this is union. So union means O. So it's O, not and. So O. So O means it's one of them, because you know that there's no number that satisfies all the all the intervals. It's only you pick one just from one of them. That's why it's O. Okay, that's how you do the problem. And these are the three type of answers that you can write. The first one is what we normally call the set builder, and that second one is the graph, the graphical version. Third one is the interval notation. So it's a graph. So the graphical solution, graphic, and the interval notation. And the first one is the set builder. Okay, so let's look at another problem. So as the next one, let's have a similar problem. So I'm going to call this hx. This is equal to x squared minus 25 divided by x squared minus 5. Let's say 5x. And we know that when you have a rational function, we only worry about the denominator. There's nothing to do with the numerator. But let's see what happened in this case, just for educational purposes. You can see that you can factor the numerator. So the factors are x minus 5 and x plus 5. In the bottom, we already did that. This is just x minus 5. You can see that the exact same factor appears this time in both the numerator and the denominator, but we are not going to cancel that. We leave it like that. We cancel that later when we talk about what they call the asymptotes. When we want to find the horizontal asymptote, we're going to vertical asymptotes. We're going to cancel that, but not now. We just leave it like that. So there are no cancellations. No So that's something we have to remember, no cancellation. So what we can do, it's very similar to the previous problem, and you can see that the two zeros are x equal 0 and 5, and we have to remove those two because we need to avoid dividing by 0. So to avoid dividing by 0, we can remove those two. So the answer is the same thing as before. That means the domain of H is exactly the same. So if you use the set builder, you can write it as x such that x not equal to 0, or and actually it's a and, not o, and x not equal to 5. But when you write the interval notation, it's go with the union, so that's a o. But here what this says that x is everything except those two. That's what it means. It cannot be x equals 0. So if you put o, now there's a problem. Which is one of them. It's not one of them. It should be both. It cannot be x equals 0. It cannot be x equals 5. So it should be and. So it's a good argument. And the answer is as the same. So let's look at the next one. Part D. Let's say we have Rx equal x squared minus 5x. I'm going to pick the exact same function, then we can avoid that factoring term every time, because that's not the point here. Like argument is the point, so we can avoid it. So again, so this is a square root function. That's an even power. If it's an even power, we know that there's a problem. So you know, make sure that this inside function produce a value which is greater than or equal to 0. So that's the problem. So that's what we're trying to do. We just set this condition. So that means we can start with x squared minus 5x greater than or equal to 0. And then what we're going to do, we're going to solve this inequality. Okay, so the next step is solve the inequality. Solve the inequality. These inequalities are very easy to solve. So what we normally do is we factor. So the step is, so I'm going to write the steps. So factor, and then find zeros, and then draw the sign diagram. Draw a sign diagram, and then find the solution. Actually, before that, yeah, to do the sign diagram, we pick test points. So I'm going to show you how to do that. So find the solution. So those are the kind of common steps for a problem like that. So let's do it. The first step is find the zeros. Find the factors first. So we have, so the factors are x minus 5 greater than or equal to 0. So this can give you other zeros, x equals 0. The other one going to give you x equal 5. Now what we're going to do, we draw the sign diagram. How to draw a sign diagram? You draw a line and then put those two numbers in the right order. So this is 0 and this is 5. We don't make any holes there, like, you know, open, close. We don't talk about that now. Now what we're going to do after we do that, you can see that there are three intervals. There are three intervals. And those in these three intervals, what we can do, we're going to pick test points in each interval. So so what is the best test point that you can find on the rightmost interval? And you can see that it is t equal 6. Now what we're going to do, after you find that, you can pick anything else like t equals 7, 8, 9, 7.1, 6.005, anything. It's just a number, like you pick like a number that is easy to work with. So t equals 6 would be the best number. Now what we're going to do, this is what we normally call the test point. That's why I use the letter t. So we're going to plug in that to the inequality, because you see that there are two factors. Just just plug in that value here and check the sign. We don't worry about what number you get. We only need to worry about what is the sign. And you can see that when you plug in t equals 6, you can see that the first factor you get 6, which is a positive number. So you see that it's positive, and that's enough. And the same thing, you plug in that 6 to the other one, you can do 6 minus 1, which is 1, 6 minus 5, which is 1, which is also positive. But what we do is we multiply these two. Since we multiply these two, plus plus means plus. So that means we mark plus. That means for any point on this interval, it should be a plus sign. It doesn't matter which point you pick. That's the argument. So now next to the next interval, you can see that you're going to plug in, you're going to pick t equal 1. That will be the best point. And if you plug in t equal 1, as before, first factor give you 1, so which is positive. The second factor going to give you 1 minus 5. 1 minus 5 means you can see it's a negative 4, so which is negative. So positive negative, that means negative because you're multiplying them. And the other one, the best point would be t equal negative 1. Do the same thing. First factor give you negative 1, that means negative. Second factor also give you negative because it's a negative 1. Negative 5 means a negative 6. So it's negative. So negative negative means positive. So this is what we call the sign diagram. You just draw the sign. You just pick the one you want. Now we look at the inequality back and check what we need. You can see that according to the inequality, what we need to be, it has to be greater than or equal to 0. That means we are looking for the one which has a positive sign. That means those two are the interval. So so we check that. That's the right interval. And then since there's an equal sign here, you are also going to include the corner points. So that means we are going to include this edge because of the equal sign. Okay. So now we know that the solution is, the graphical version is this one. That's the graphical solution. So we can also write the set builder like this. So if you want to write the set builder, so domain of R is, how to write it? It is x such that x is less than or equal to 0. That's the first one. Or, and you can see that it can be and. There are no common values to both. So you can say, oh, you write in word, and x greater than or equal 5. You can see x has to be bigger than or equal to 5 or less than or equal to 0. So that is the set builder notation for this one. And if you want to write this in the interval notation, it's again very easy. Start with negative infinity, go up to 0 and including 0 and put a union, and then start at 5 and go to infinity. So that is the interval. So those are the three solutions, three ways to write the solution. Okay. So again, the union means O. That's the union. So that means O, because it's one of them. It can be both. We pick values from one of them. Good. So let's look at the next problem. So I mean, any problem like this, you just do it this way. So how about the next problem? So next part E. So let's look at this problem. Let's say st equal 3 minus 2t, the sixth root. So we learned that when you have an even root, they all behave like the square root function. Whereas we have even root, the sixth root. So they all behave like square root function. That means the condition that we need is this has to be greater than or equal 0. So we're gonna start with that. So we're gonna say that we can say since y equal x, the sixth root is defined only for x greater than or equal 0. So we're gonna put that condition here. So it doesn't matter what even power we have, we all behave the same. So we're gonna say 3 minus 2t greater than or equal 0. Now the question is how to solve this one. So be careful with this one. We just do the same way like how we normally solve inequalities. So we're gonna isolate the t term. That's the whole point. So we're gonna move 3 to the other side. So when you change the term to the other side, you simply change the sign. That's how you remember it. So we are not gonna do like minus 3 minus 3. We don't do that anymore. So what we do, we change a term from one side to the other side, simply change the sign. That's it. So now the thing is that you have to divide by -2. So you have to be very careful with this one, because when you divide or multiply by a negative number, so I'm going to do that in the next line. So when you divide or multiply by a negative number, so what happens is going to switch the sign of the inequality. So it's not 0, sign of the inequality. So it's going to be -3 divided by -2. You can see now, so it switched the sign. You can see Swiss sign. Now what happened? This get cancelled, so you get t on this side. The other side, -3, -2 become 3 halves. So that's a solution. So very simple. So t has to be less than or equal to 3 halves. So then we can write the solution. So that means the domain of S is t, now it's t, which is a real number. You can add this extra information such that t has to be greater than or equal 3 halves. As I said, build the notation, and you can simply graph this one. And then also the interval notation is very simple. So it goes to -infinity all the way up to 3 halves, and including, so with the close interval, not the open, close interval. And if you also want to graph it, it's also very easy to graph. So this is a solid dot, this is included, and then so this is 3 halves. So what happened, you're gonna highlight, or yeah, that's a set, so you can mark the set. So that's including the point. So that's the set, and you can see it's a smaller, that's why to the left. So left means small, right means large. Good. Okay, so let's look at the next problem. So f, so let's say we have gx equal two functions now. Let's say 3x plus 12 square root divided by x minus 3. So now this is not a rational function, because rational function, they have to be polynomial. It's a rational like function. So this is what we can say is rational like function, because it behave pretty much the same way as rational functions, but these are much more worse than rational functions. So let's look at the two things. The one condition comes from the denominator is just a simple condition. We try to avoid dividing by 0. That means x cannot be equal to 3. So that's the only condition coming from the denominator. But from the numerator, since this is a even root function, so the variable what you plug in here has to be greater than or equal to 0. Okay, since this is a square root function. So that means the condition that we're going to do is we're going to say 3x plus 12 has to be greater than or equal to 0, because this is a square root function. Now we can solve this like before. So this is very easy. 3x, move the term to the other side, divide by 3. This is a positive number, does not change the inequality. You get -4. Okay, now we know that x has to be greater than or equal to -4, but at the same time x cannot be equal to 3. So that means if you write the set builder, it is x, which is a real number, such that we line we call such that x greater than or equal to -4, and because to satisfy both conditions, and x not equal to 3. So now the question is how to draw this one. So let's draw this first. It will be much easier to write the interval notation. So how it looks like, so it says that there are a few problems now. So -4, and there's an equal sign, that means you can draw the solid dot. So -4, but it says that you have to remove 3. So at 3 there's an open dot. So what it says is bigger or equal than -4, but not 3. So that means if you start at, so it's bigger, that means it's going to go to the larger side. So, it's going to go -4 all the way up to 3, and stop at 3, and then you again start after 3. That's how it looks like, the graph. So not 3. So that means this can help you to find the interval notation. So how the interval notation are going to work? You start with -4, start at -4, go all the way up to 3 and not 3, so you make it open, and then union, and then go start at 3 and go all the way up to infinity. So that's how you write the interval notation. And please note that, see, there's like a close, and then these are open, and infinity is always open. So there's a few things that you need to remember, but that's how you solve this problem. So let's look at one more problem. So let's say we have k u, the variable is u now, 3u plus 12, the fifth root, divided by, let's say, x minus 3 as before. So you can see that this, actually no, x is u, so u minus 3. So you can see that this problem is very similar to the previous problem. Only difference is now we are taking a odd root. But we know that if you take odd root, the domain is all real numbers. That means there are no restrictions from the numerator. So no restrictions. So that means we only need to worry about the denominator. So denominator only says that u not equal to 3. So that means this problem looks much simpler compared to the previous one. It looks very difficult, but it's very simple. So so that means the domain for this problem is simply domain of K is simply u in R such that u not equal to 3, and that's it. So how to write it? You just remove 3, that means negative infinity up to 3 and union 3 to infinity. So that's how we write the 2. And then also if you want to write the interval, what do? You put the 3 and open, because it's not there, that's 3, and then everything else. That means this side and that side. Good. So we can do one last problem. How about this one? Let's say I. So let's say fx equal x minus 3 square root plus 4 plus x fourth root, something like that. So you can see that there are two functions now, not just one function but two functions. So if you have two functions, what we're going to do, we're going to find all the values that satisfy both of them, and then you can see that they are all even roots. That means the condition is whatever inside has to be greater than or equal to 0. Again, whatever inside has to be greater than or equal to 0. So what we do, we solve both and find the common region. So solve for both inequalities and find the common region, because it has to satisfy both. So find the common region. So that's how we do. So so let's do the rest of the problem now. So we have fx equal x minus 3 square root plus 4 plus x fourth root. So what we do, as we discussed, this has to be greater than or equal to 0. This has to be greater than or equal to 0. So we solve them separately. So let's look at the first one. So x minus 3 greater than or equal to 0. This is very easy to solve. This says that x equal greater than or equal 3. The second one says that 4 plus x are greater than or equal to 0. In other words, x greater than or equal to negative 4. Now the condition is this has to satisfy both of them, because it's not just one. It has whatever the x value should be able to plug into both of them. It should be in the domain of each. So that means there's an AND condition. It's not a O, it's an AND condition. So that means, so the question is how to graph it. So when you have two like that, when they are in the same direction, x has to be larger than the larger one. Because if x is larger than the larger one, is automatically larger than the smaller one. So that means since 3 is bigger than negative 4, so we can write it like this. So what I'm going to, we can combine them. So there are two ways to do it. One way is like look at the graph. So if you look at the first graph, so what this says that, so you have a 3, and then it's going to go to the right side. That's the first one. That's 3. The other one says we have negative 4, and that's 3 here. It says that it says again it's larger, so it's going to go to this side. Now what happened? You can see that if you pick a value like 0, if you pick a value like 0, like here, that value is only bigger than -4. So it does not work for, it's not bigger than 3. That means this value is a incorrect value. So you can see that if you pick a value which is bigger than both, that means it's 3 or more, it's automatically satisfy both of them. So the another way to do this is try to draw this line below the other. So so it's not in a scale. So you can draw it below the other. So that's, I'm going to call it -4. It's not in a scale. So now you can see that. So what we can do, we can look for the common region. So we draw this like that, and you can see the common region start here. So that's the common. So that's the common region. It should be common region. So that means clearly see that it has to be 3 or more. So that's the other way to do it. Just draw one below the other and pick the common region. So that means the solution is simply so we can say x such that x greater than or equal the larger one. So larger than the larger. That's how we remember it. So this will be like a interesting problem. So what do you think about this one? So this you can try this as an exercise. So let's say I'm going to slightly change this problem. So this one is 3. Let's change the inside. So let's say it is 4 minus x. And then you can see that it completely changed the direction of the inequality, and it also so it's not like that. So it's going to be common. It will be, your solution will be in between. So see whether you can get the answer for this one. So that's how you solve. That's how we find domains of certain functions. So in a separate video, we're gonna do some practice problems. So I'm gonna post those problems here, and you can practice them for extra experience. So let's look at them now. Now try to do these problems as practice problems, and you can find the solutions, complete solutions in a separate video, so you can watch them later.